Let us try to look at the performance of data link layer technologies such as switches from the application viewpoint. Although the application layer is at the top and the data link layer is the second last layer, these two layers are not directly connected. However, as we shall see, the impact of the performance at the data link layer directly affects the performance at the application layer. In this module, we shall focus at how data center networks operate, how load balancing is performed, and what are the implications if the switching speed is not good enough to provide connections between the hosts in each rack. In this module, we shall introduce the concept of load balancing in data center networks. We'll look at the typical hierarchical design proposed by Cisco, and we'll look at some of the problems with their solutions. The two references I've chosen are VL2, a scalable and flexible data center network, and DoIT, cloud scale load balancing with hardware and software. The second reference in particular includes figures and concepts which give you an insight into the problems which emerge in data center networks. What are data centers and how they form a network? Google, Microsoft, Facebook, and Amazon, they create massive data centers. Each data center houses tens of hundreds or tens of thousands of hosts. Each host is like a server which is installed in a rack. These data centers provide unique and custom-made cloud applications for the users. So each user is interested in having a very personalized experience, whether it is searching, emailing, social networking, and so forth. In data centers, each rack that comprises multiple hosts is connected to a switch called TOR or top of rack switch that connects the hosts in the rack. These hosts are connected to one another, typically at the speeds of 1 gigabits per second. And all these hosts are connected to their top of rack switch. This top of rack switch is subsequently connected with other switches in the data center. All these comprise a data center network. From the user point of view, each application that is offered as a cloud service hosted at a data center is visible to the user through a publicly known URL and IP address. The client sends the requests and receives the response. From the outside, the client is seeing just one data center, but on the inside, there is a swarm of servers. Some of these servers are lightly loaded and some are not loaded at all. And some of the servers are extremely or heavily loaded. So we need a kind of entity called load balancer. So the client requests should go to the load balancer, and the load balancer forwards the requests to the servers which are not much loaded. That is why such load balancer is also called a layer 4 switch with NAT capability, because on the outside a public IP address is known, but on the inside it is private addressing scheme. Let's look at the problem that happens in hierarchical routing. We see that the client sends the requests coming in from here, and on the inside we see that the requests are forwarded through the load balancer to the respective racks where the servers, also known as the hosts, are installed, which not only communicate with the client but also within themselves. For the sake of example, let's understand that between the switches for example, this switch and this switch, there is 10 gigabits per second inter-switch connectivity, and within the rack, these hosts have 1 gigabits per second internal connection. Now, imagine that we have rack 1, 2, 3, 4, 5, 6, 7, and 8. 1 wishes to talk to 5, 2 to 6, 3 to 7, and 4 to 8. If that's the requirement, for instance, if we have a host in rack 1 that wishes to send some data to rack 5 before sending a response back to the client, and so forth, the overall bandwidth utilization is going to be overloading the bandwidth availability with each switch. Let's see that more descriptively. Imagine that we have 40 simultaneous flows between 40 pairs of hosts in different racks, such that 10 hosts in rack 1 send flow to corresponding host in rack 5, 10 flows between pairs of hosts in rack 2 and 6, 3 and 7, and 4 or 8 also send data. When we have 40 flows over 10 gigabits per second links, that is, for instance, A to B link and B to C link, each link offers only 10 gigabits per second, but we have a requirement of 40 gigabits per second. So essentially, each of these flows is going to have 250 megabits per second in the exterior top of rack switching. That means we are only getting a quarter of what the hosts could get if it were the same rack. In order to solve the problem, people have come up with various solutions. One of the most obvious solutions is that we provide more interconnectivity. Now, this particular switch, which is connected to 4 of these top of the rack switches, now is connected to more number of tier 1 switches, such that if the requests are sent in, or the replies are sent out, or if the paths are to be established between the top of the rack, these can be routed from here to here. In such way, the overall bandwidth requirement can be met and fulfilled.